Okay, I think it's time we can start now the presentation. So do the brief introductions. Good afternoon, everyone. Today, the Adam Seminar has the great pleasure of welcoming Dr. José Manuel Vicent-Luna. He obtained his Master's in Science and Technology of Colloids and Interfaces from the University of Pablo de Olavide in Seville, Spain in 2013, and his Ph.D. on Physical Chemistry in 2018 in the same institution. Currently, he's a postdoctoral researcher at Eindhoven University of Technology in the Netherlands. And his research focuses on molecular simulation of multifunctional nanomaterials and complex liquids for energy-related applications. His aim is to combine simulation techniques from quantum to classical methods, covering a wide range on the atomistic scale to solve scientific challenges in material science applications. Once again, welcome, Dr. Vicent. Thank you so much for being here with us today, and please feel free to start our presentation now.
Good afternoon, everybody. Many thanks first for the introduction. I would like to thank to the organizer for inviting me to this seminar and giving me the opportunity of talking a little bit about part of my work. So as been said, I have been combining during my trajectory different type of molecular simulation techniques to study complex processes on different materials and different applications. And from all of them, I have chosen today this talk based on ionic liquid materials. From all the systems I have studied, I have particular interest on these materials. I like them a lot, and I think they are in line with the interest of the host institution. And I think in this previous time has been talking a lot about ionic liquids. So first of all, let me recap a little bit and start again with the main definition of ionic liquids. So in this sense, room temperature ionic liquids, not or simply ionic liquids, just to simplify, are liquid salts, normally in room temperature, which are composed by organic cations and organic or inorganic anions. So this material has raised the attention of many researchers in the previous years because they have desirable properties that can be used in many applications. So to name a few of these properties, they exhibit very low vapor pressure. So in the sense that they have low volatility, so they are environmentally friendly and normally non-toxic. So they are very good solvents because they have high polarity, so they can dissolve many species. So they show to very high ionic conductivity. They have been reported to be thermal, chemical, and electrochemical stability. But one of the main properties that compensate this, the previous one, is the high tunability. So we can combine these cations and anions in different ways. So the properties can change a little bit. So for this reason, they have been used in many applications during the past year. For example, they have been used as catalysts or in green chemistry, in extraction and separation of gases, in electrochemistry. I will focus this presentation in some of the examples in batteries and supercapacitors. They have been used as lubricants, as drug delivery in pharmaceuticals, in biotechnology, but they are always surprising because recently in the last year, they are emerging in the new applications. So ionic liquids now are being proposed to be used in devices in optic and photonics, in the semiconductor industry, and I'm very interested on these topics. So we have a very large number of compounds that can be created by combining different cations and anions. So we could say that ionic liquids can be tailor-made to be used in different applications depending on their properties, because when we combine different cations with different anions, we have a new compound, and this new compound has similar or different properties to the previous ones. So here there is a small example of which are the most common cations and anions on ionic liquids. There are much more, but these are very recognized in literature. So rough numbers can be said that we can have 100,000 conventional ionic liquids combining the ones that we see here. For example, the cation is just a simple representation, but this change can be extended. So one of these families can give you to many possibilities of ionic liquids. And just with the fact of increasing the chain of one of these cations, you can convert a hydrophilic to an hydrophobic material. So if we go to more numbers, and we can estimate possible combinations just to pure ionic liquid. So pure ionic liquids are composed for a single cation and a single anion. We can talk about millions of possible combinations. But this is not the end, because we can combine multiple of them at the same time. We can have one cation, two anions, otherwise around, different 2 or 3 cations, 2 or 3 anions. This gives us mixed ionic liquids. So in this mix, we have another change, because when we have mixtures, we can play with the concentration, how many of each type we combine. So then we can call that we have 10 to the power n mixed ionic liquids, because we don't know the real number that we can get in this. But there is more, because ionic liquids have improved to be excellent materials when combined with other type of materials. So you can mix ionic liquid with many types of molecular species materials, and then you are switching, most of the times improving the properties of these new materials. So the number of possibilities is still increased. So at this point, it's very clear that we cannot use experiments to describe all of these possible combinations. Either it's not clear that we can do it with molecular simulation, but at least molecular simulations can play an important role of the study of these ionic liquids. So let's talk a little bit about the molecular simulations. So all of the people working in simulation might be tired of seeing representation like this that has become very popular in the recent years, which represent a multi-scale approach. When we represent the time that we can simulate in our systems, the size of the system that we can simulate, and put more or less rough terms the techniques that we can use. So we have, in the lower scale, the highest accurate techniques, can be the quantum mechanical calculations. There are different types of them. And then we can pass directly to classical simulations, when we can study very bigger systems compared to the quantum one, but still in the atomistic scale. So these two techniques cover, I would say, more than the 90% of the published literature in general in simulation, not only for ionic liquid, but for everything. After that, we have other kind of simulations, like processes, numerical simulations, thermodynamic modeling, but at the end, that we are looking for to complement, to design new experiments, or to understand what's happening in the experiments. So it's not fair, or it's not reasonable just to give all the important only to different techniques in the atomistic scale. So here you can see that these are the most popular techniques, but somehow they don't have much overlap between them. So in here, we only, in the sense of ionic liquids, we can simulate a few pairs with high accuracy. And here we can simulate many of them, but we lack of accuracy replicating many of their properties. Or, for example, we cannot reproduce the electron. We cannot study the electron with this type of simulations. But fortunately, there are something in between. They are not highly popular, but there are many things that have been developed in the recent years with the aim of fixing this overlap, or bridging the gap between these techniques, which allow us or increase the size and time scales that we can use in quantum calculations, or improving the accuracy of classical simulation. So let's make a zoom in this part, in the atomistic scale, and put some names on it. So now the quantum mechanical calculation, the most typical one or the most standard one is density functional theory. There are others, but this is the most used in literature. On the high end of the graph, we have the classical simulations with conventional force fields, because other ones that I put here in the middle are also classical, but they have some specifics or names, some appendix, because they have more specific application, which could be reactive, polarizable simulation, machine learning simulations. And now there are other types of quantum-based simulations, quantum-based because they can describe electrons, but they are not purely quantum. They might be quantum semi-empirical, they are mostly called, which can be density functional time binding methods. So in the talk of today, most of my results come from classical simulations and then somehow complemented later with a specific method of density functional time binding, which I would like to explain a little bit more in detail. So small overview here in terms of this molecular simulation technique is, if we start with the most accurate ones, we can agree that the density functional theory, the DFT, has a very good balance between the number of atoms that we can simulate, the properties that we can get from them, and the size and time scales that we can get. So very high computational cost to simulate some complex ionic liquids. For example, for pure system, it's okay, but when we start mixing different ionic liquids, so then the size of the system must be high. So sometimes not affordable for density functional theory. So in essence, we have start with many body problem with the electrons surrounding the ions, and what different DFT says is that we are describing this many body problem in a sense of electron density. So the main message here is that the energy of a system is an energy that is depending on the description of this electron density. So when setting up what quantum calculation like this, we have different options to say how to describe the atomic basis, the function of that we use, the numerical quality, some of the physical effect, like relativistic effect, or many other things. So they are settings that we can do, but we are not imposing, or it's not normal that we develop the method by yourself. The normal thing is that we use already implemented methods in normal software. If we jump to the other side, classical simulations, classical with force fields, we can reach very large systems, still in the atomistic scale, but much, much larger systems, but at the expense of losing accuracy and losing an important part, which is the description of the electrons. So these force fields are constructed by giving the description of the energy of the system. We have to describe the interaction. We have to give an identity to all of our atoms, all of our molecules inside of system. Normally, the most simplistic representation is like this, when we divide the energy of our system between bonded and non-bonded interactions, while the bonded take care about the atoms that are connected by chemical bonds, angles, torsion, improper torsion, so giving a few functional forms to describe these bonded interactions. And the other two terms take care of the van der Waals interaction or the Coulombic interactions, which are highly important in ionic liquids because they are charged particles. Normal examples of potential that take care about the van der Waals interaction can be the Lennard-Joule or the Buckingham potential, which are based on these simple functions depending on the interatomic distance between molecules and some of the adjustable parameters. So the relativity, so the accuracy of these force fields depends, the accuracy of these simulations depends on how our model can describe experiments or not. If we have a very good force field, we can rely that our results will be very good, but sometimes it's very complex to get this force field. I haven't used explicitly for ionic liquids and this type of simulation, but I know that there are modifications to these classical force fields in terms of making them reactive or polarizable, and there are a few good force fields to describe ionic liquids, including polarization terms. So the essence of these force fields is exactly the same as the classical force field when we construct the interaction energy of a system by including additional terms to describe different specific processes mechanisms. For example, polarizable force field includes a term that takes care of the polarization, not only based on point charges as the classical one. Reactive force fields make a modification of the bonding structure, and we can create or break bonds. So we can continue, and we cannot ignore the fact that the artificial intelligence or machine learning is entering also in the molecular simulation world. And in a few years, probably we have to handle all these simulations because they seem to be very promising. So even I have not, I only have used this for a very little time. I think they can be very promising. In this talk, I'm not going to talk about the machine learning, but I consider that it was wise to give some insight about this type of force field. When I see machine learning simulations, I specifically use this type of machine learning interatomic potentials. So it means that we are running the same simulation that with the classical force field. We are solving the motion equations, but the energy of the systems comes from a machine learning method. So how it's more or less done this? We have the description of a molecule. The molecule has some chemical composition, and the architecture learns normally from DFT how it has how the interactions are depending of the atoms that we have around. So we have many molecular species with different atomic environment. So all of this gives a very wide set of energies. And using normally a neural network, the architecture learns how this atom has to behave when they have other type of atoms around. So for each atom, we have atomic energies that are linked with this, and the summation of all the energies give us the total energy of the system. That this is the main property that we are always looking for. So let's say that the energy of a machine learning simulation comes from the learning of DFT calculations. So now I promise you to talk a little bit more about the density functional tight binding, because I think it has some benefits and it can be very, very interesting, because it can speed up the DFT calculations, it can describe electrons, and can connect with large-scale simulations. So there are many things that we can do. So the base of these techniques is that this is an approximation to DFT. So this is not strictly quantum mechanical calculation, but this is an approximation to. So it's normally taken from the energy of the DFT as we can make a Taylor expansion of this energy, taking a reference electron density with small perturbation. So we have different terms, different orders. And there are multiple techniques that do that. So you can divide these terms, assign different type of function to describe these processes, and have different techniques. So specifically, I have been working with this one, the extended tie binding method, GFN1 extended tie binding, because the parametrization of this is not straightforward. It costs time, so it's very complex to parameterize this, and this came directly with the elements of the periodic table. To the most competitors, DFT work, which produce application. So the energy of this method is an approximation of DFT, has 4 different terms in energy. So here is something similar that the classical force field. We have an electronic, repulsion, dispersion, and halogen bonding terms. to have an example, let's see a little bit in more detail to have more clear concept what it is and what it is done here, is that the GFN Hamiltonian is composed of these 4 terms, and for example, this is the repulsive term. So you see that this is an exponential decay when we have that the repulsive term is as a function of the interatomic distance, like the Lennard-Jones, and some kind of parameters, theta, alpha, k. So these parameters depends on the properties of the atom. So there are parameters of the atom like the sigma or the epsilon in the classical potential. So we switch a little bit these parameters and we have some representation like this. So the purpose of this term is just to add a repulsive barrier. So to avoid that 2 atoms comes very near to each other. The following term is the dispersion one, which is the common dispersion terms used in DFT calculation. Instead, this is the D3 dispersion term used in standard DFT calculations and has an expression something like this. So we have a dispersive term, a repulsive term. The last one, the halogen, is just a correction for a few elements. So I don't think it's very, very important. It might be important for some specific interactions, but has a representation like this, a few parameters and an equation. But the core of this method is the electronic part. This is the difficult part. So I'm not going to enter in detail, so don't worry that much watching this, but if we want, we are aiming to describe the electronic properties of a system. We don't expect to have the same kind of function easy one. So in principle, this is the a summary of the electronic part of the Hamiltonian. We are not going to enter in describing this part. So the main message that I want to give you here is that differently to other methods, in other DFTB method, you pre-compute all interactions, and when you run the simulation, this is you take the values like from a table file. Here is slightly different because you have trained the model, you pre-compute the interactions, you develop these functional forms, and what you have is a series of parameters here giving rise to the identity of each atom in the method. I have highlighted in different colors, so the blue ones are parameters of the method, so they are all the same for all the elements. The red one are element-specific parameters, so each element has their own parameterization, and there's only one in the whole Hamiltonian, which is intended to make some correction to the interaction between 2 different elements, A and B. So in principle, it's a very complex description here, but the good thing having these parameters is we can modify. So there is nothing that hinders us to modify these parameters for a given application. So we can generate a training set based on DFT calculations and use a smart algorithm to feed these parameters again to improve the accuracy for the application that we are interested in. So in this presentation, I have not used any modifications, so I just have used the original DFTB method developed by Grimm a few years ago. So after this description of the simulation techniques, we enter in a brief explanation of some I have got in the previous year. So this is was my first paper using ionic liquids for my thesis. So I was studying the behavior of ionic liquids as electrolytes for dye-sensitized solar cells, and the problem that I have at that moment is that I had not a good classical force field to reproduce density and diffusion coefficients of the elements at the same time. So I was having with ionic liquids combining imidazolium and pyrrolidinium cations, and pure system. And for imidazoline, there were available some forfeits that I have only to tune a little bit, but I didn't found any proper forfeit for pyrrolidinium. So I had to develop myself. I tuned the Lennard-Jones and the charge to get this type of curves where there are a comparison between the densities as a function of the temperature of the ionic liquids changing the chain length of the cation. So we can see here that the agreement is very, very good, and also with special attention of running transport properties at the same time to get a proper description of the diffusion coefficient. So here you can see the diffusion coefficient of the imidazolium cations with the Tf2n anions for different temperatures and changing the length of the cation. So we can say that this forfeit is accurate enough to compute density and transport properties of these materials of ionic liquids. So this solves a little bit of a debate if a classical forfeit can show high accuracy describing many different properties. So here, what we see in the left-hand side, in the right-hand side, is also a comparison between experiments and molecular dynamics, but the diffusion coefficient, not the ionic liquids, but some ionic charge carried within them. So here we are not comparing exactly the same magnitude, because I compute the cell diffusion coefficients, and from experiment what I got is the collective diffusion coefficient. So there is a thermodynamic factor between them, but the agreement is correct. So this is a combination, this is a mix between ionic liquid and a common solvent. So this was the first time that I don't use pure ionic liquids alone. So I also mix them with common solvents. So the main conclusion here, apart from the application, is I developed a forfeit which was good for reproducing the density and transport properties of pyrrolidinium cation with this anion. So this led me to a second study, because some of my collaborators were interested on this type of electrolyte, but not for solar cells, but also for it was the emergence of lithium and sodium ion batteries. So these studies were become very popular at this time. So I had a forfeit. So why not to study the behavior of the systems too? So the main research question here is there were a few papers before which show that the conductivity of the electrolyte decreases when you increase the concentration of sodium or lithium. So the main system is I have an ionic liquid and I include different concentration of a salt based on lithium or sodium. So what's happening here is these are simulation experiments. So my forfeit was able somehow to reproduce very well the conductivity, the ionic conductivity of the system. So if we focus here in this site and we make a representation like this, we have that the total conductivity of the electrolyte, the black line, decrease when you add salt. So in principle, you can guess that the responsible for this depletion of the conductivity are the sodium or the lithium cations that we introduce in the system. But when we divide the total conductivity and the contribution of every species, we see that the contribution of sodium, or in the case of lithium, is almost negligible. So what it drops the conductivity is the contribution of the ionic liquid species itself. So why, if I add sodium or lithium, the conductivity decrease if this has negligible effect on it? So after some studies, reviewing literature and analyzing our simulation, we found that the main responsible for this is the creation of this type of complexes or cluster in which the anion make a strong solvation of the lithium or the sodium metals. So we were not sure if our forfeit could reproduce these things, because the forfeit reproduced very well the density, diffusion, and conductivity, but we were not sure at that moment if it also has a very good representation of the structural behavior in the atomistic scale. So for that, we run DFT calculations of the same electrolytes and compare the structural properties of them. So here is an additional validation that the force field work decently when we have combination between classical molecular dynamics or ab initio molecular dynamics. I must say that the ab initio molecular dynamics took longer to run than all the rest of the simulation for the same project. So it's very, very computationally demanding. But at this moment, we have a proper validation that with the classical simulation, we can take a look of the local structure of these things. So in a deeper look here, what we see is the radial distribution function between the metal and the oxygen atoms of the solvating ion. Here, on the other side, we have the radial distribution function, but between the metal and the nitrogen, the central nitrogen of the atom. So we give you a more different behavior of the radial distribution function. We were able to discriminate into two different contributions with the peak and lower radius are responsible for this conformation, which is called Byzantine conformation. So a single metal is interacting with two oxygen at the same time. On the other side, we have this representation, which is a monodentate conformation, which is the metal interacting with a single oxygen. So, in summary, what we have here is that the conductivity is slightly higher for monodentate conformations, a little bit smaller for bidentate conformation, and it depends on the radius of the metacation. Sodium is bigger than lithium, so it has more surface to accommodate the anion. So, the next step was to study how this cluster affects to the total structure of the electrolyte, and we have here the radial distribution function between the anions itself. So we see here the shadow part is that when we increase the concentration of salt, we see that the emergence of a peak here. This is because the presence of these clusters that they travel together in the electrolyte, so it's lowering the diffusion coefficient of the total system. So this is the reason why we have more sodium or more lithium, we have more cluster of bigger size, and this is why the decrease on the conductivity that we can see in the experiment. So later on, we switch to other type of systems. In this case, I had experimental collaborators that came to me with a challenge. So we have seen before that mixing a small amount of salt to an ionic liquid can change a lot the structural arrangement of it and change it still the properties. So the basis of this study is that we have an ionic liquid, and when we mix with another solvent, acetic acid in this case, we are transitioning from one ionic liquid to a deep euthetic solvent, and they didn't know why. So this is an experimental representation. When we have this specific concentration of acetic acid added to the ionic liquid, this is converted to the deep euthetic solvent. So in this study, I combined DFTB with classical simulations, try to understand what was the reason of this. So we see that we have a cation, we have the anion, and somehow the acetic acid is solvating the structure of the cation, of the anion, sorry. So taking a deeper look of the trajectory of the molecular dynamics, we can try to find which are the most representative interactions in this study. So first, we can see that the solvation of the chloride anions by this solvent. So there is a type of hydrogen bonding created here, which is very clear. So we study the radial distribution function between chloride and the hydrogen atoms of the acetic acid. So we have this type of representation, and the line represent the equilibrium geometry given by the DFTB calculation. So integrating this curve, we can have the coordination numbers, and from this we can extract the average number of hydrogen bonds in this type of system. So we can see that the numbers of bonds linearly increase until 3, 4, and then it changes behavior when you grow. So normally, when you have a change in the slope in colloidal science, it means that there are very big structural changes. So something is happening here between 3 and 4. We can move to another interaction. Now the interaction between the solvent itself. So we know that acetic acid can form dimers, can form strong hydrogen bonds when they are in bulk. So we are looking for them. So now the representation is a little bit more complex, the Rayleigh distribution function between oxygen and hydrogen in the acetic acid gives you to this profile. The first peak is the hydrogen bond in acetic acid. So two molecules that are hydrogen bonded between themselves. So we see that there is no peak at the beginning, and the peak emerges somehow. So again, the vertical lines come from the equilibrium structure from the DFTB. The other lines come from the analysis of the trajectory of the molecular dynamics. The second peak is the intramolecular interaction, so hydrogen and oxygen within the same molecule. And the third one is the interaction between hydrogen and oxygen when they have in the middle a chloride. So this will be practically this thing. Again, we have a very clear path or very clear criterion when we have to put. And we see that the acetic acid within itself doesn't form any hydrogen bond until we have until we have more than 4 molecules together. So again, 3, 4 is the K in this study. Again, we can have more or less the same representation when we study the interaction between the cation and the acetic acid. Again, repeating the story, we have a transition along 3 and 4. If we go to the analysis of the interaction between the cation and the anion itself, this is a little bit more complex. So because there are many more conformations, there is not a single one. So with DFTB calculations, if we just use a single ion pair, the representation cannot be compared directly with the molecular dynamics, because this is the so-called gas phase. So these conformations are not found in the molecular dynamics. But when we increase the number of ion pairs, we can have parallel conformation, anti-parallel conformation. So the geometry of these changes, and we can correlate these geometries with the results found in the molecular dynamics. So from literature, we know that amine and chloride can form some kinds of hydrogen bonding, and we can divide this into contributions. So the hydrogen bond and weak bonds. So both of them can be represented somehow here, and also we have exactly the same than before. In about 3, 4, we have a phase transition. So what's happening here? So the reason of ionic liquid has suffered a transition to a ditotectic solvent is because the acetic acid is fully solvating the chloride, but they still are not forming hydrogen bond between themselves to be able to behave like a liquid acetic acid. So this is an example where only mixing a simple ionic liquid with a simple solvent, we can change the properties of all the system substantially. So what will happen in the case, and we have much more complex system, much more complex representation, much more complex mixtures. So this comes from the last part of the result of this presentation. So again, my collaborator came to me a few years ago with some challenges because they have an electrolyte for supercapacitors composed by what the so-called trisolvent in salt, which is combining 3 different types of solvent with one ionic liquid to study the electrolyte and supercapacitor. This was this formulation. Like here, when we have all of this part of the electrolyte is fixed, and we add different amount, which is the variable part of acetonitrile. So this was not the end. They didn't know how this system behaves structurally. And after a few years later on, we make another try, because we read in literature that combining different cations with different anions, you can switch the properties of the ionic liquid. So this is a second case when instead of having a single ionic liquid, we have a combination between two anions, the BF4, and this is the same anion that I mentioned in the previous paper, the TF2M, but with other notation. They are also mixed with the three solvents. But it is not the only change that we can do, because in the introductions I told you that we can mix many things, because here we have a very concrete composition of this electrolyte, which is not random. It was based on the study of the pure ionic liquids, the dual one, but we can also make modifications to the concentration of this one. And every time that we make a modification on our system, we find that there are different performance from for the electrolytes, for the electrochemical conversion, and because the properties of the whole system changes. So some examples are that at first I had to validate the force field somehow, because I didn't develop force field for this type of jobs, but I took force fields that were previously validated for density and diffusion coefficients in the literature, but not with this type of mixtures, because we didn't know if this the force field can handle when you pass from the pure system to the mixture. So here you can see the comparison of the pure system, the density, and also from the mixture. So we can trust that the force field is good enough to study this complex mixture. So first of all, we have to identify which are the main interactions between the elements, because these are very complex mixtures with many species and many atoms. So everything can interact in principle with everything. So again, I use DFTB, GFN, extended time binding simulations to help me with identification of these main interactions. So what I did here to get this type of cluster, these are the optimized structure. This is not a representative snapshot. This is the lowest energy structure of these ones, because I create about 1,000 random configurations. I sort them in energies, and I got some valuable information of this system. So you can say, okay, this guy has been talking about the DFTB, but how we know that this is reliable or it can reproduce other things? So here I have some kind of validation comparing the DFTB with reference DFT. So this is the overlapping in geometries when you make a geometry optimization of one of the ionic liquids and the other. This is the potential energy surface. So the relative energy as a function of the distance between the center of mass of them, and this is the energy of dissociation. So the energy the energies at the minimum of this representation compute with the DFT and with the DFTB. So we can see that this is very suitable to reproduce these systems. So DFTB is not only for supporting the classical simulation, but we can extract something information from them. So we can see more or less here that the balls, the red and the orange ones, are separated somehow from the blue ones. So the blue ones and the green ones are the solvents, the others are the cation and the anion. So the important thing here is even a high concentration of solvent, you are not breaking the ionic character of ionic liquid. So cations and anions and somehow together. So what we study here is the first coordination self of all the species surrounding the cation. This is one of the most important features, the local structures around the cations. Comparing these two scenarios, when we have only one ionic liquid and two ionic liquid with the same amount of solvent, we have the first coordination cell. And the main thing is that when we have only one ionic liquid, the total number of solvent increase. When we have both of them, the total number of species decrease with concentration of the solvent. So the next thing to see is this blue square here is higher than in this case, which is the summation of the coordination of the two anions. So we can conclude that the more presence of anions around the cations in dual ionic liquids than the pure ionic liquid. So we can see that the big anion TFSI protects the tetrafluoroborate anion from the solvent. They come together to the cation, and this leads to ionic charge which is localized around the cations. So the electrochemistry of this sample is much better than this because the ionic charge is more localized together, and the solvents cannot break the ionic structure of the ionic liquids. Again, with the last step is what will happen when we change the concentration of our anions. So we mix two different anions. And in principle, we can think that in pure tetrafluoroborate or in pure TFSI, if we have like 3 species surrounding the cations, the mixture should behave similarly. But this is not the case. The case is that we have a non-ideal representation like this, that intermediate concentrations give you a maximum in the coordination cells of the cation. So we can conclude from the studies that the number of anions around the cation in dual ionic liquid strongly depends on the anion molar fraction. So you cannot study certain concentration as it is. You need to cover a wide range of compositions to be able to get which is with the best performing electrolyte. So similar concentration of TFSI and BA4 favors the highest coordination. So again, the same conclusion. So the ionic charge localized around the cations improve the electrochemical efficiency of this electrolyte. So there has to be somehow some electronic properties that are affecting this type of behavior. And thanks to the DFTP, we can also compute these electronic structure properties. For example, we can compute the HOMO and LUMO orbitals of the mixtures. So this is for one of the ionic liquid, this is for the other. And then we have here a transition changing the anion from one to the other. Here we see in red the binding energy, how strong is the interaction between them. And here the HOMO-LUMO gap. Why the HOMO-LUMO gap is interesting? Because it can be related with the electrochemical window, operational window in this kind of electrolytes. So after the study of these atomic orbitals, we can conclude that the cations contribute to the LUMO orbital in all the mixtures. From intermediate concentrations, the tetrafluoroborate do not contribute anymore in the electronic structure of these mixtures. In the low concentration, BA4 tetrafluoroborate share contribution with the cations to the HOMO orbital. So at the end, the highest contribution to the electronic charge transfer is given by the TFSI anion and not from the BA4. To finish this presentation and to show the potential of the DFTB methods is that we can also simulate other optoelectronic properties like the absorption spectra. Here I compare DFT on top of DFTB absorption spectra as a function of the different wavelength, and even there are deviation between one to another. The shape of the absorption spectra is very similar, and the good thing of this method is what I told you before in the methodology, that we can tune the parameters of this method to increase the accuracy of the method. And one of the tools that we can find here is that we can represent all the electronic energy levels. We can know how all the atoms influence the electronic structure of this species. So with all of this information, we can train, based on a reference data given by DFT calculations, a method that can allow us to study not only structural features of compound, but also more electronic structure calculations. So to conclude the presentation of today, we have seen that molecular simulation using validated force field. I say validated because not all the force fields are good enough to reproduce the experimental observation, but the ones that are validated has been proved effective in understanding structure and transfer properties of ionic liquids and some derivatives. We can combine classical simulation with quantum or other semi-empirical methods, not only for the validation, but also to provide additional insights into the complex behavior of complex mixtures. So among others, the GFN extended time binding methods appears to be an excellent method that can bridge the gap between the large-scale molecular dynamics and the more fundamental DFT calculations. So the tunability of this method makes it promising from the future to study complex systems for sizes that are affordable to conventional quantum mechanical calculations. As an outlook, I will miss a more detailed assessment of this method for predicting more electronic properties in a very wide range of samples, and to be able to decide if further refinement of the parameters is needed or the method works fine as it is developed. So this is everything that I wanted to mention, and so thank you for your attention. And I want to thank also to all the collaborators that I have to develop these studies. So thank you again, and if you have any question, we'll be happy to try to help.